In problem 5, we're going to look at a very useful approximation called Stirling's approximation. So we're going to take some n, which is an integer, positive integer, and we want to find an approximation for n factorial. In part 1, we're asked to plot the function f of x equals natural log of x. And so you can do this with MATLAB or Wolfram Alpha. Here I've plotted it between 0 and 1,000, and the most important points to notice is that it's always increasing and it's concave, which means that whenever you draw a line between 2 points, the function, natural log of x, will be above whatever line you drew. It has to be a straight line, but you can pick any 2 points and this will work. In part 2, we're asked to use the plot to explain why the natural log of 1 plus the natural log of 2, and so on up to the natural log of n, should be greater than or equal to the integral between 1 and n of natural log of x dx. So first, let's note that we can write the integral from 1 to n of natural log of x dx as the integral from 1 to 2 of natural log of x dx plus the integral from 2 to 3 of natural log of x dx, and so on, up to n minus 1 to n natural log of x dx. And so essentially what we're going to do is we're going to compare this term to the natural log of n, and and this term to the natural log of 1, this one to the natural log of 2, etc. Actually we're going to compare this one to the natural log of 2 and this one to the natural log of 3. So, for example, in each case, we will compare the integral of a to a plus 1 of natural log of x dx to the natural log of a plus 1. So for this case, this would be a equals, this is the a equals 1 case. So here we can draw the natural log of a plus 1 is this high, and this will be width 1. Then this has area, natural log of a plus 1. Then we can plot the natural log of a plus 1 and natural log of a, and so this goes from a to a plus 1, and this will have area equal to the integral. And you can see, if you draw these pictures better than I have, so this is also width 1, by the way. And here, for example, if we take natural log of a plus 1, extend it over, then this is the box that we had in our first picture. And so clearly the area of the integral, the area that represents the integral, is much smaller, or at least somewhat smaller, than the box representing simply the natural log of a plus 1. And we see this down here in figure A, which is drawn much more nicely than my figure. So now we see that in each case, the natural log will be less than or equal to, the integral will be less than or equal to the natural log. And so for each of these terms, let's just write it out here. So we know that natural log of 1, which by the way is 0, so it can be paired with nothing, that's fine, plus natural log of 2 plus dot 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 plus natural log of n will be greater than the integral from 1 to 2 plus the integral from 2 to 3. There's a natural log of x dx in here that I'm not writing, plus dot 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 plus integral n minus 1 to n natural log of x dx. This is inside each of the integrals. And so these integrals turn into 1 to the n natural log of x dx. And this is actually greater than or equal to. So now we've shown the property. So now we want to show that the natural log of 1 plus natural log of 2, etc. up to natural log of n is less than the integral from 1 to n plus 1 of the natural log of x dx. So again, we'll write out the integral by splitting it up. 1 to n plus 1, natural log of x dx is from 1 to 2, natural log of x dx, plus the integral from 2 to 3, again natural log of x dx, plus all the way up to the integral from n to n plus 1, natural log of x dx. So, as before, we'll pair them up. So this will compare to the natural log of n. And we notice because we've split these up, now we have n chunks. So actually this guy needs to be compared with the natural log of 1, and this guy with the natural log of 2. So now we're comparing the natural log of a to the integral between a and a plus 1 of the natural log of x dx. So here we have the picture similar to before. This is height natural log a, this is height natural log a plus 1, and this will be width 1, because this is a and this is a plus 1. So this area is given by the integral. But then the natural log of a can be represented as the natural log of a times 1, so it's the area by this box here, which is clearly smaller than the area represented by the integral, which means that the natural log of a will be less than or equal to the integral between a and a plus 1 of natural log of x dx. So essentially, when we write it out, we end up with kind of the opposite situation as before. So natural log of 1 plus natural log of 2 plus natural log n. Each of these will be less than or equal to integral between 1 and 2 plus integral 2 and 3, integral n to n plus 1 of natural log of x dx, which altogether is 1 to n plus 1 natural log of x dx. And actually, I was wrong, we don't have equality here. So it's strictly less than. And then we're done. And just as a side note, actually, this picture here is depicted in this picture, which I stole from the official solutions. So just in case you find that drawing to be a bit nicer. So now we want to know why the natural log of a plus the natural log of a plus 1, all of that divided by 2, so essentially the average of the two, is less than the integral from a to a plus 1 of natural log of x dx. So we can see, for example, that the area represented by the integral will again be this curved shape from natural log a to a plus 1. And this will be width 1. And we can represent, so this is for the integral of a to a plus 1, natural log of x dx. And we can represent this average as we give a half width box. So this will be width 1/2 to the natural log of a, and a half width box to the natural log of a plus 1. So this area will be half natural log a plus half natural log a plus 1, which is equal to this natural log a plus natural log a plus 1 all divided by 2. So you take this area, and it's not immediately obvious how these two pictures compare. But essentially we can visualize turning this picture into this picture if we take for example, so this will be natural log of a. This is natural log of a plus 1. And we took this portion here and moved it to here. So when we're done, we end up with a representation of the area that looks more like this. Excuse my drawing skills. And when we compare that to this picture over here, we see that it actually follows this line, and so the area represented by this average will be less than the area represented by the integral. And actually, I think that these pictures are much better than my horrible drawings, so you should definitely take a look at those in the official solutions. So now we want to use part 2 to prove that n factorial is greater than or equal to e times n over e to the n. So this seems a bit confusing at first, but since we're told to use equation 1, what we'll do is we'll write out the natural log of n factorial is the natural log of n times n minus 1 times dot 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 down to 1. And because of the properties of logs, we can actually write this as the natural log of n plus the natural log of n minus 1 plus dot 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 plus the natural log of 1. So this we know from equation 1 would be greater than or equal to the integral from 1 to n of the natural log of x dx, which is equivalent to x natural log x minus x evaluated between 1 and n, which is n times the natural log of n minus n minus 0 minus 1. So this is equal to n times the natural log of n minus n plus 1. Now again, from properties of logs, we can write this as the natural log of n to the n. We can also write n as the natural log of e to the n, which may seem a little bit weird, but the natural log cancels out the e and you just get n. And we can similarly write 1 is equal to the natural log of e to the 1, which is just the natural log of e. So then substituting these in here, we get this is minus natural log of e to the n plus the natural log of e. Now using log properties again, we get that this is equal to the natural log of n to the n times e over e to the n, which is equal to the natural log of e times n over e to the n. So therefore, n factorial is greater than or equal to e times n over e to the n. Similarly, in part 6, we want to show that n factorial is less than or equal to e times n over e to the n using equation 2. So again, with that hint, we're going to write out the natural log of n factorial is the natural log of 1 plus the natural log of 2 plus up to the natural log of n. So this is another way to write this, is to group the natural log 1, natural log 2 up to the natural log of n minus 1 plus natural log of n. So this here we know something about by equation 2. We couldn't keep the natural log n in because we have this index going up to n plus 1. So we know that this natural log of n factorial, just repeat it here for clarity, is less than or equal to the integral from 1 to n of the natural log of x dx plus the natural log of n. So now we just evaluate this integral, and we get that this will be x natural log x minus x evaluated from 1 to n plus the natural log of n. So this will be n natural log n minus n plus 0 minus 1 plus natural log n. Combining terms, we have n natural log n minus n plus 1 plus natural log n. Again, we can write this n natural log n as the natural log of n to the n. We can write this n as natural log of e to the n. The 1 is a natural log of e, and then this natural log n sticks around. So now combining these, we get the natural log of n to the n over e to the n times e times n, which is the natural log of e times n over e to the n. And therefore, n factorial is less than or equal to e n over e to the n. In part 7, we're going to use equation 3 to prove that n factorial is less than or equal to e times square root of n times n over e to the n, which is a tighter upper bound than the one shown in 6. So again, we'll start out with natural log of n factorial is natural log 1 plus natural log 2 plus natural log n. So since we need to use equation 3, we know that we need to have some sort of natural log a plus natural log a plus 1 over 2. So let's try writing this as natural log 1 over 2 plus natural log 1 over 2. So that'll be just a natural log 1 plus natural log 2 over 2 plus natural log 2 over 2, and so on. And what we see is that if we group this one, then this one will go with a natural log 3 over 2, etc. We'll have, so let's just, natural log n over 2, natural log n over 2. So if we continue the groupings, this one will be grouped, and this one will be, the very last one will be on its own. And another thing to know is that this guy's just equal to 0, so we can get rid of him. So, using equation 3, we know that this will be less than, so this was, we go from a to a plus 1, so we go from 1 to 2 of natural log of x dx, and then we'll have it from 2 to 3, and so on, all the way up to n minus 1 to the n, natural log x dx, and then the natural log n over 2, which is still hanging out because it didn't get paired up. So when we combine all of these integrals, we have it going from 1 to n, natural log x dx plus natural log n over 2. We can evaluate this integral. So again, we get x natural log x minus x from 1 to n plus natural log n over 2. So this will be n natural log n minus n minus 0 minus 1 plus natural log n over 2, which we can write as n natural log n minus n plus 1 plus natural log n over 2. And rewriting these with log identities, we get natural log n to the n minus natural log e to the n plus natural log e, and natural log n over 2 is 1/2 times natural log n which is natural log of n to the 1/2, which is natural log of square root n. So this is plus natural log square root n. And then overall we have, again combining everything, natural log of n to the n over e to the n times e square root n. And therefore, n factorial less than or equal to n over e to the n, e square root n. For part 8, we're just asked to plot the ratio between n factorial and the square root of 2 pi n times n over e to the n. And this plot is shown here on the right, and essentially what we see is that n grows larger, this ratio becomes essentially 1. So this is a reasonable approximation for a reasonably large n, and in fact it takes off, I mean you could say n equals 10, it's probably accurate. So in part 9, we're asked to apply the simpler version of Stirling's approximation, which is given in part 8 as n factorial is approximately equal to n over e to the n, to rewrite n choose k. So n choose k is equal to n factorial over n minus k factorial times k factorial, which, using this approximation, will be approximately equal to, so the n factorial turns into n over e to the n, the k factorial will turn into k over e to the k, and the n minus k factorial will turn into n minus k over e to the n minus k. So let's simplify this a little bit. So this will be n to the n over e to the n times e to the n minus k over n minus k to the n minus k times e to the k, k to the k. And again, we can further simplify this. So e to the n minus k times e to the k, e to the n minus k times e to the k is just equal to e to the n. So these terms disappear, and we get n to the n over n minus k to the n minus k times k to the k. We can further write this as n over n over n minus k to the n minus k. So now we've used up this n minus k to the n minus k, and all but k of the n's, and we put those remaining k n's in a n over k to the k. So you can see we have n to the n minus k times n to the k is n to the n. And yeah, so we haven't lost anything here. And now if we say that m is equal to k over n, then we can write this as 1 over 1 minus m to the 1 minus m times n times 1 over m to the m times n. There's just a little bit of algebra in between, but you can check it for yourself. For part 10, we're asked to plot n choose k1, etc. as functions of n on a log-scaled y-axis for various values of m. So we have m1 is k1 over n, which should be equal to 0.25, etc. And so what we see here is that these functions are linear when plotted on a logarithmic y-axis, and that the functions for m1 and m3 overlap with each other. Finally, we want to know the slopes of the functions in this plot. So the slope will be log 10. For example, if you do a log 10 scaling of the axis of n choose ki, so this will hold for any of the i's, over n. Slope is rise over run. So this will be approximately, we'll pull out the 1 over n, and this will be log 10, and using our previous results, 1 minus mi, this to the 1 minus mi times n, 1 over mi to the mi times n. And this is equal to, if we pull out the n, we get an n coming out of this logarithm because all of the everything inside is to the power of n, so we can pull that out. We also have an n over n, so this will just cancel. And we have log 10 of the stuff that's left, so 1 minus mi minus I. And then we can actually write these guys as negative. So negative will apply to everything. 1 minus mi, we bring the power out. Log 10, 1 minus mi. So the negative comes because we took this 1 minus mi and we took, this 1 over 1 minus mi, and we raised it to the power of -1, so that flips this guy up to the numerator, and the -1 comes out in front of the log. Plus mi log 10 mi. Again, same trick here. So this will be the slope of each of these lines. And so from here we can just plug in what the mi is. So for example, when we have m1 equals 0.25, the slope will be negative on everything, 0.75 log 10 of 0.75 plus 0.25 log 10 of 0.25. Those are parentheses. And so this is, so the slope is approximately equal to this. And this is about 0.244. So you can do this for each of the mi's in turn. And you can check the written solutions for those, but I'll just let you know. So the slope for m2 will be 0.301, and the slope for m3 will be 0.244. And you could have also used, for example, base e to scale your y-axis, in which case all of these log 10 terms would turn to natural logarithms instead. And so for those, the slopes in order are 0.562, 0.693, and 0.562.